Yes, sir.
Yes.
Of analog to digital conversion, and we saw that the signal, if it is in the range between Vmin and Vmax, we can break this range into several smaller uh, levels, smaller parts, and equal smaller parts. And the more number of smaller parts we have, more number of divisions we have, the more number of bits will be needed. So if we uh, further, we also saw that the signal which is to be digitized, it is compared with these levels so that you can identify what is the level. So you get something like a triangular pattern over here. You can see that if it is in this range between 0 and 1 volts, as in this example, then you get a particular bit combination 000. If it is in this range between 1 and 2, then you get 001. If you are in this range between 2 and 3, you get 011, and between 3 and 4, you get 111. So you see that this pattern goes on building up like this. You can go on adding more and more uh, comparators. So uh, if you want more bits, say suppose, uh, so after obtaining this bit pattern, we again further need to convert it to a binary representation, binary count as a uh, bit representation, because this is not bit representation, this is just a pattern, it's just a gray code pattern. So this pattern has to be uh, converted to a binary representation. That is what is done using this code converter. Of course, you need a trigger in order to initiate the uh, analog to digital conversion, and the values that are obtained as the outputs of these comparators are latched over here in these respective latches, and they're passed on to the code converter circuit immediately. And because you make use of a combination logic circuit here at the code converter level, you immediately get the bit pattern V0, V1. In this case, we have taken just a 2-bit analog to digital converter. We also saw that here we did not make use of the digital to analog converter as was used in the ramp method and the successive approximation method. Uh, it was instant. The conversion was instantaneous. You could just press the trigger and immediately the bit is available here. The digitized value is available here. But because of the large amount of hardware that is involved in this method, it's very expensive. It's very fast, but it's very expensive. And we saw that just for 2-bit representation, we needed 4 resistances. We required 4 minus 1, that is 3 comparators and 3 latches. If we had just to increase this bit representation by 1 more, that is, if we wanted a 3-bit representation, so 2 raised to 3, that is 8. So we would have had to have 8 resistances here, so that we could divide it into 8 equal parts. We need 7 comparators, 8 minus 1, that is 7 comparators and 7 latches. Okay, and then we need a logic circuit, a combination logic circuit, to convert the output of these 7 inputs, from these 7 inputs, to 3 bits. Okay, so this is how the process of flash conversion takes place. It's expensive, no doubt. And then because it is expensive, one can use the idea of multiplexing. Yesterday I had made a slight error while constructing this, so I've modified it some time back. And we have the inputs coming from different channels these channels could be connected to sensors, and these signals which are available on these channels, they could be coming from sensors after signal processing, that is after filtering, amplification, offsetting, etc. So they would all be available on these channels. But we have only one analog to digital converter. That is because it's a expensive one, flash ADC, it's expensive. So we are going to have this analog multiplexer here, and one can multiplex this. Today you have this can be just done by switching. So you can switch these channels, which channel you want to acquire from, and accordingly that channel gets connected to the flash ADC, and then the process of conversion is immediate. So you can do the process one by one for all these channels and obtain the digitized values here, this flash converter. Yes, yesterday I had made a mistake in the symbol of this. It's an analog to digital converter, which is the reverse of the digital to analog converter symbol. So I had made that mistake. I have corrected it in this sketch here. Now let us try to set right a few things. Let's try to augment our understanding. We'll take an example. So I've picked up an example from one of your assignment sheets, which will be posted to you shortly. Uh, the problem is, given an 8-bit analog to digital converter operating over a voltage range from 0 to 10 volts, what digital output code would correspond to each of the following sensor values? This is the question before us. Okay. So we have the analog voltage range from 0 to 8 volts, and it has to be digitized using an 8-bit analog to digital converter. So if the digitization takes place, whenever the digitization takes place, we will represent it using 8 bits like this, as shown here. Now, corresponding to each of these values, which are sampled, corresponding to these voltage levels in the range of 0 to 10 volts, what will be the bit pattern that will be produced? This is the question. So it's similar to what we have done in our lecture on DA, digital to analog converter, as well. Here also we can use mapping. So let's say that let us take 0 volts here, a signal 0 volts. Okay, and here let us say that we have 10 volts. So this is our range of analog. So this is the range in which our signal lies. So we could say that this is actually the range for our analog signal. It can lie in this range. And for the digital part, let's say that 0 volts is 0 in the decimal system. Okay, I'm writing it deliberately. I'm writing it in the decimal system, and because it is 8-bit representation, you see, you can go from 0 to 2 raised to 8 minus 1. 2 raised to 8, okay, and minus 1. So this is your range, and this will be therefore 256 minus 1, that is 255. Okay, so you will have 255. So 0 to 255. So you can go from 0 to 255 when, uh, in fact, when it is 0, you have a bit pattern as 0, 0, 0, 0, 0, 0, 0, 0. And when everything is 1, you have 1, 1, 1, 1, 1, 1, 1, 1. So the lower part, let's say, is 0. And here we have 255. 55. Let us say that this is the representation, the digitized value, and let's call this digitized value as n. We could, okay, we can call it as n. There's no problem. Now, the relationship between this is actually linear. So let us fit a curve here. So 0 volts corresponds to 0 here, and this corresponds to, this is also to the base 10, because it's also in decimal. So we'll take this linear relationship, 0 volts corresponding to 0 and 10 volts corresponding to 255. So it's a linear relationship. Okay, and that's the reason why if you have any voltage in this region, let's say you have some voltage corresponding to this, that is some arbitrary value, then the corresponding digital value that is obtained will be here. Okay, so we'll write it as, the coordinate of this will be Vs, and corresponding to this Vs, the digitized value is n. Naturally, it's an 8-bit integer. Okay, n is an 8-bit integer. So here, say this is n, and this is Vs. Okay. So what is this relationship between n and Vs? Let's try to write it. We can write down the equation for this. So n, we can write down the coordinates first. So corresponding to this point, the coordinate is 0 volts and 0 to the base 10. And here we have 10 volts and 255 to the base. So n minus 0 divided by Vs minus 0 will be equal to 255. I'm not writing to the base 10, minus 0 divided by 10 minus 0. So this is in order to obtain the equation of this line, and so we know that n will be equal to Vs multiplied by this, that is 255 divided by 10. So 255 divided by 10 Vs. Of course, you can simplify it. I've just okay. Let's do that. So this is 5 5s are 25, 5 1s are, and this is 5 2s are. Yes. So this is the relationship. Now let us apply this. So corresponding to the Vs of 8 volts here, if we apply Vs of first of all, we have 0 volts, 0 volts. So when Vs is 0 volts, what will be the bit count? So when Vs is 0, this will get multiplied by 0, n will be equal to, so n will be equal to 0. Okay. It is an integer. When Vs is equal to 1 volt, what will be n? 51 divided by 2. So this will be 25 by 25.5. Okay. Now we will see what this is going to be. When you represent it in terms of a box like this, we want the digital representation here. Let us see if we can compact it a little. Yeah. So this becomes, in this case, everything is 0. So can you tell me what will be the digits over here? What should we fill up over here? Here we will have everything as 0, 0, 0, 0, 0, 0, 0, 0, 0. All 8 bits are zeros because it's corresponding to 0. This is the digitized value. Okay. This is n to the base 2. This is, let me write it here. This is n when you are expressing it in terms of binary. And this is n when you are writing it in terms of decimals. But you see, this decimal 0.5 gets excluded. Now, what should you write over here? You have 25.5. What should you have over here? So, to answer that question, you have two possibilities. It could be 25 or it could be 26. It can't be 24, it can't be 27. Okay. So you have an option, either you digitize it as 25, as 24, sorry, 25 or 26. This is the option. Okay. So if you represent it as 25, So you can make use of the same thing what we did in the last few lectures. One, two, just go on doubling these weightages, 8, 16, 32, or you can also write it. So these are the weightages for each of these boxes. Now, if you're going to start with 25, you can't have 32 here. So these digits are going to be 0. Okay. Then you have 16. You'll put a 1. 16 plus 8, again you'll put a 1 because 24. 24 plus 4 is not going to work because that will be 28. You can't put it here. Then you can't have here also because 24 plus 2 is going to be 26. So 24 plus 1. So this is the combination that will work. 16 plus 8 plus 1. Okay. So you will get 25. If you want to represent 26, then you will have to make this 1 and make this as 0. So this will be for 26. So these are the options that you have. Now it depends upon what is the algorithm which you have followed. In the one which we used for uh, our flash conversion, say in the flash converter technique, when we had a signal between 1 and 2, between 1 and 2, so we had the bit pattern, or it was digitized as what? Uh, let's say if you had 1.5 as your signal, then 1.5 was compared with 2, and then you got 0 over here. So this did not work. So you had to leave the digitized value at 1 itself. That means on the lower side. So here also, if you follow this algorithm, we'll find that we'll have to go for the lower side. Okay. So this is the choice that we will have to exercise. In the same way, let's take 7.8 for example. So when you have so if you have 7.8 here, I think we can do it afresh. So VS 7.8 and corresponding to this N that you get. Can you tell me what is N? N10 corresponding to 7.8. So 51 by 2 into 7.8. Can you tell me what is this going to be? Yes, quickly.
198.9, sir.
198.9.
198.9.
198.9. So we have to represent it as 198. Got it? So we will two options. Either you write it as 198 or you write it as 199. Okay. And if we follow the algorithm that we use for the flash conversion, then it is going to be 198. Okay. So this is the pitfall of the digital to analog representation. It has to represent it in discrete form. So it can't choose these intermediate values. So 198. So 198 has to be represented here. And you can do it like this. So place a 1 here. Let us do that quickly, just for you. Or you can use even the method of division, So see, just you can also use method of division. Let's use the method of divisions for a change. So 198. So you divide it by 2. Okay. 2 9s are 18. 2 9s are 18. Remainder is 0. Then again divide by 2. Get 2 4s are 8 and 2 9s are 18. Remainder is 1. Then again divide by 2. Get 2 2s are 4. 2 4s are 8. Remainder is 1. Again divide by 2. You get 2 1s are 2. 2s are 4. Remainder is 0. And again 2 6 are 12. Remainder is 0. Then 2 3s are 6. Remainder is 0. And again 2 1s are 2. Remainder is 1. Again 2 zeros are, remainder is 1. And then you have to just topple this entire block. Okay. Just topple this entire block. So okay, as you topple it, you will get this value as 0 1 1 0 0 0 1 1. Let us just check whether what we have done is correct or not. So we are going to add here 128, 128 and 64 and 4 and 2. 4 and sorry. 4 and 2. That corresponds to this bit pattern, and when you add it, you get 12, 12 and 6, 18, carry over 1, 9, 1. So your by the division method also you got this as 198. So this is to the base 2, and this is equal to 198 when represented in decimal. Okay, this is when 198 is represented. So this is how you can do this problem. You can also do it for 5.5. We have just taken a few representative values. Does anyone have any query, any question so far? If you don't have, then we'll proceed with one more problem. To take one more example, time permits. Let us take another example. I have got some of your assignment questions here before me. You can try out. I'll be giving this assignment sheet to you. So, of course, there are times when we can also make the ranges bipolar, like -5 to +5. Okay, and you have to work it out. So there will be some things which you will have to read on your own and determine. So what is the Shannon's sampling theorem? Okay. What is the sample and hold? What do you mean by aliasing? So many of these things are explained quite nicely in the book by Alciator and Histad. I want you to read on your own also and to do it, so that No, it's, you don't just stick to what is being taught in the class, you just copy it and reproduce it in the exam. That should not be the attitude. So there are several problems here, and uh, I think we can conclude this part of our discussion here. Uh, a few problems only in this assignment sheet, not many. So I think there should not be much of a difficulty. So let us, if you don't have any question, I'll conclude the lecture here for today. It's okay? Does anybody have any further query? You can ask me.
Excuse me.
Yes, please go ahead.
So, why did we say that the relationship is linear, or is it an information?
Is it a?
I mean, is it a fact that it is like that, or is there any reason why is it a linear relationship?
It is a linear relationship because you see, you are going. If you see the what you are doing here, you are going from 0 to 4. Okay. So you are going from 0 to 4, and 0 to 4 means you are making use of, you are going from 0 here to a maximum of 4 here. Okay. And while you are going from 0 to 4, what are the possible combinations that you can have corresponding to this 2-bit register? You can have combination going from 0 in the decimal, okay, up to 3. Okay. So when you are in the range between 0 and 1, so between 0 and 1 volt, you will have the digitized value as 00. When you are in the range between 1 and 2, when your signal is in the range between 1 and 2, 1 and 2 volts, this range, you will get this bit pattern, and corresponding to it you will get this, and this corresponds to 1. Okay. I'm sorry, this should have been the decimal, not CB. CB in the decimal. This is 3. This is the binary representation. This is in the decimal. When you are in the range between 2 and 3 volts, you get the bit pattern 10, which corresponds to 2. And when you are in the range between 3 and 4 volts, this off. So when you are in this range between 3 and 4 volts, you are here in this range. You will get the bit pattern as 1 1, which is 3 0. So you can see that as you add a step, okay, your numbers are increasing. This is also increasing in equal steps. This is also increasing in equal steps. What is this relationship called? It's a linear relationship, right? Does that answer your question?
Yes, sir. Thank you.
Yes. Any other question? Any other question? If you don't have any other question, we'll conclude here for today. Okay.